and Avogadro's law, which are kind of really the same thing in a way. Law of combining volumes is going to deal with volumes, so milliliters and liters and things like that. Avogadro's law, when you think about Avogadro, we think about molecules and moles and things like that. So it's going to be that kind of relationship there. It says here, law of combining volumes. Scientists concluded that in chemical reactions, gases combine in very simple proportions. The law states that when gases react, the volumes of the gaseous reactants and products, so the volumes of the reactant and products, okay, measured at the same conditions of temperature and pressure are always in whole number ratios. And basically what they're saying is there's a direct, as we know, there's a direct relationship between N and V. Okay, and that's what we're going to focus on again today here. So when you think about PV equals nRT, if temperature and pressure are all the same stuff, right? Pressure, temperature, R is the same. Well, gee, that only leaves two variables left. Okay, and we kind of talked about this with molar volume because this is kind of another extension of that. Look, there's a direct relationship between V and N, right? If we're going to have the same pressure and temperature for these gases, the more moles we have, right? The more moles that we have, the more space it takes up, the more volume we're going to need to keep it at the same pressure and temperature, right? More molecules you have, the more pressure you usually have. However, how are we going to combat that? We're going to give it more volume. So we're going to expand that, okay? So there's a direct relationship between V and N here. And basically, the questions are going to look, there is a few questions associated with these, and you'll see some on your test as well. And they're pretty straightforward if you can kind of, well, I guess if you understand whole ratios, whole number ratios, okay? In this particular case, I'm going to get you guys to fill in a little bit here. All these things are measured at the same pressure and temperature. And it'll say that in the question just to make sure that you guys understand that since it's the same pressure and temperature, V and N have a direct relationship. So let's go ahead and write this in here. Hydrogen gas and oxygen gas give us water vapor, water gas, basically. Okay? So we know that, okay, hydrogen gas and oxygen gas give us water vapor. So this is a particular equation we're going to focus on for this example. Now we could do it with any gases, for example, but this is just one that we had picked out for an example. Okay. Now, as far as this chemical equation that I've written up here is not balanced. So one of the things that will help you for sure is if you can balance chemical equations, and if you can't, ultimately that's Unit 4 stuff, which we will do a lot of. However, this is Science 10 technically as well, so it's probably something we should be able to do. Here we got two hydrogens, we got two hydrogens. Here we have two oxygens. Here we only have one oxygen, so I'd put a 2 there, of course, to get two oxygens. Now I have 4 hydrogens there, so I'd put a 2 there, okay? And that would be balanced. You don't need to put the 1 in here, but I'm going to just because I want to illustrate my example here. So basically it's when we look at this equation, it takes 2 H2s combined with an O2. They recombine to give you 2 waters. Okay? And actually, by the way, they'll show you this on the last page here if we skip right here. So look, here's your H2s, okay, the white ones. Here's your O2s. So to recombine, you need 2 of these. So 2 of those would pair up with 1 of those to give you a molecule that looks like something like that there. Okay? So you can kind of see that there. We'll come back to that later though, but okay? So once again, okay, balanced chemical equation. Rearranging of atoms there. All right? Now, back to our example here. So take a look at the blue numbers there. It's telling you that basically, you know, if I had 2 H2s, so just 2 simple molecules, kind of like this here, HH and HH, right? And I combine that with an O and an O, that would give me HOH and HOH. Oops. Like that kind of thing, okay? So 2 of those, 1 of those O2s, okay, gives me 2 of those H2Os there, basically. That's basically what it's telling you. To make it a little more, like that's pretty small, obviously. We wouldn't usually talk about that on a molecule basis. We talk about that on a mole basis. You know, so 2 moles, 1 mole, and 2 moles basically is how many number of molecules you'd have there. All right. Look at the numbers below here. Do you see a pattern to those numbers compared to the balanced chemical equation? And if you do, what is it? Look at the numbers below there. Look at the volumes. What do you notice about the volumes in this particular case? Look at the blue numbers. Look at the volumes. Do they match up? See. Yes, exactly. Hydrogen's double oxygen, and this is double the oxygen as well. Look, this is a 2 to 1 to 2 ratio. Look at the volumes. 2 to 1 to 2 ratio if you simplified the volumes, yes? 50 to 100, that's times 2, yes? 1 to 2. Yeah? Okay? This is as hard as it gets. Don't make it harder than it is. 1 to 2, 1 to 2. Okay? Why? The pressure and the temperature are staying the same for all these gases. The more moles you have, the more molecules you have, the more volume you need to have. Right? This one particularly has 1 mole would take up 50 milliliters of space. So here's my 1 mole of gas, 50 milliliters. Gee, now I have 2 moles of hydrogen at the same pressure and temperature. How am I going to do that? Well, how am I going to keep the same pressure and temperature, considering I have 1 mole and it takes up this much room? If I have 2 moles, well, I need twice the volume, yes? Right? So that's what this ratio is doing for you. It's telling you the volume of gas. There's a direct relationship there. Look, I just showed it to you right here. There's a direct relationship between N and V if everything else is the same. Okay? P, R, T, all the same. So V and N are the only thing that can change here. The more N you have, the more volume you need to have to keep it at the same pressure and temperature. So this is in fact a 1 to 2 and a 2 ratio, just like this is a 1, 2, and a 2 ratio. The next volume I gave for you here was, once again, 1 to 2, 1 to 2. Yes? So it's always in that same ratio. So what is the question going to be like on the test, for example? It's nothing more than this, I'll tell you right now. It looks exactly like one of these questions here. And it'll say, if I wanted to make 200 milliliters of water vapor, if I wanted to make 200, how many milliliters of hydrogen should I use to make 200 milliliters of water gas? And the answer would be 200. Yes? Why? Because look, 2 is to 2, as 2 is to 2. Well, actually, I probably should go this way. 2 is to 2. Yeah? So if I want to make 200, I need 200. Right? If I want to make 2 moles of this gas, I need 2 moles of this. If I want to make 200 milliliters, I need 200 milliliters here. Yes? If the question was, I have 200 milliliters of water vapor, how many milliliters of oxygen should I use? Your answer would be 100. Yes? Okay? Right? Because look, 2 to 1, 2 to 1. Yes? The more volume you have, well, the more moles you have, the more volume you need. Okay? That is it. That's as complicated as this gets. Okay? All right? So, we'll look at another example here, and I'll show you something else you can do based on this stuff here. Yours are lined up a lot better. Mine didn't. So I'm just going to put some arrows here just so you guys can kind of... like I said, mine didn't line up as well as yours did. Ammonia gas, okay, gives you hydrogen gas and nitrogen gas. This would be called the decomposition reaction, which we'll look at in Unit 4, okay, decomp. simple decomposition. All right. Now, I don't expect you guys to know what ammonia gas is. That's fine. Okay. But do you have to be able to balance these numbers? Well, you should be able to. Okay. NH3 is ammonia gas, so you guys can write this up, but you have to write this in here, guys. Otherwise, we can't really do the question here. Okay, so that's basically what they're telling me. Ammonia gas, NH3 gas, gives me hydrogen, which of course is H2, and N2 gas, nitrogen gas. Now, some of you guys will look at that equation and be able to balance it, no problem, right? That's something we should be able. That's, once again, like I talked about earlier, that's probably science 10. We should be able to probably do that, okay? So we could do it based on that. But look, if there is, in fact, if these are all at the same pressure and temperature, okay, then that means N and V are directly tied to each other. What did I do with the last one? I said, hey, now this is another thing that you need to be able to do with this, guys. I said, hey, look, if this is a 2 to 1 to 2, in other words, if I know N, I can predict V's, yes? Because they go together. If I know V's, could I find N's based on the same principle? Sure you can. If I knew this and this and this, could I in fact turn around and say, I know the balanced chemical equation therefore? Should be able to, right? So look, in this example here, right? Look at the volumes I've given you here for this. Can you work backwards? Can you take those volumes and say, gee, if those are the volumes, could I figure out the balanced chemical equation based on this? Probably could, right? Assuming, of course, they're all at the same pressure and temperature, which they will be. They have to be, otherwise we can't ask you this question. Okay, it's a little more complex than that. So look, you could use these numbers here, okay, 150, 225, and 75. Those numbers are a little bit not quite as easy to work with. But look, most of us know 25, 75, and 50. If I wanted to come up with a balanced chemical equation based on these volumes for this balanced chemical equation, could I do that? Sure. Pick the lowest common multiples, right? Let's see. 25 goes into all those numbers, yeah? So I could say if this was 1 for 25, for 50 it should be 2, for 75 it should be 3, okay? Based on those volumes. There's a direct relationship between the volume and the moles, right? Does that balance out? Sure it does. Look, 2 nitrogens, 2 nitrogens. 6 hydrogens, 6 hydrogens, okay? Or you could just, of course, balance it as well. That works too. But that's also nice to know that it works either way. You could take the volumes and figure out the balanced chemical equation, or the moles or the molecules, or you could take the moles and the molecules and figure out the volumes, okay? So that works there. Once again, you know, the questions are going to be, can you predict what, you know, how much ammonia gas I'd be using to decompose? Let's say I end up with, oh, I don't know, 60 milliliters of nitrogen gas. How many milliliters of ammonia gas did I use to achieve that 60 milliliters? And the answer, of course, would be what? Somebody. Yeah. Sure, 120, right? So I would have had to use 120 milliliters to give me 60 milliliters of that, right? And by the way, you could also figure out the hydrogen here if you had to. Obviously, this is, by the way, 1 to 2, 1 to 2, yes? Okay. Look, 1 to 3, 60, 180 probably, yes? Okay. So at the same pressure and temperature, those gases have to match up with their volumes, basically. Volumes of the gaseous reactants. Okay? So I got 3 quick practice questions for you guys to do here, and we'll do those and we'll go over them here today. But this one involves the first reaction that we did today. This one's the second one. This one you'll have to come up with your own equation for. Okay, it talks about nitrogen gas and oxygen gas gives you nitrogen dioxide. So you should be able to write that out probably and then come up with some numbers. They even tell you some numbers here for this one. So they actually tell you that this and this and this, okay, all go together. Okay, so go ahead and do those real quick and we'll talk about those in a sec here. Alright, so first one, obviously like I said, you can use the equation from before. I'll probably give you the equation obviously for the test and whatnot, or I might give you the volumes and you can figure out the equation. We got both sets here for that. Okay, so 3 is an example of that. 1 or 3 is probably good questions to know how to do obviously. What volume of water vapor forms, so basically what volume here forms when 250 milliliters of hydrogen reacts with 125 milliliters of that. Okay. Well, we can see, of course, that this is a 2-to-1 ratio, 2-to-1. So how much would I get here? Well, 2 to 2. Your answer should be 250. Right? Make sense? Yes? Okay. Or you can say, well, 125 to 2, 1 to 2, 125 to 250, right? But it's all based on the same ratio, whatever, okay? This one here, what volume of nitrogen gas forms when decomposition of ammonia gas produces 15 milliliters of hydrogen? So if I got 15 milliliters of hydrogen here, okay, what volume of nitrogen gas forms? Okay, so you just have to be careful in this case here. You do have to read the questions very carefully because we need to make sure we put these numbers in the right spot so we can kind of compare them, right? If we put 15 here or here, obviously the answer is going to change and it's going to be wrong. So we just got to make sure we read the question very carefully and line up the stuff and make sure you answer the question. So what volume of nitrogen gas, that's what I'm looking for. When the decomposition of ammonia, so decomposition of ammonia produces 15 of hydrogen here. So 15 of hydrogen there, okay? What should I get for nitrogen there? 3 to 1, so 5, yeah? 5 should be your answer for this one, 5 milliliters, okay? So hydrogen gas, 3 to 1 ratio, 15 to 5, yes? Okay, 3 to 1, 3 to 1. A chemist performed an experiment that determined nitrogen gas reacted with oxygen gas and once again formed nitrogen dioxide gas. Now I know that that's something we probably should be able to do. That's science 10. Okay, that's a formation reaction, or you guys maybe called it synthesis. I don't know. We call it formation now, but whatever, same thing. Okay, that's a simple formation reaction. They, once again, in this particular example, they've told you that what volumes react. So they say 125 milliliters reacted with 250 milliliters, and it formed 250 milliliters of this gas here. So guess what? Based on those numbers alone, some of you guys can balance the chemical equation, sure. But if you can't, look, 125, 250, 250. Gee, that looks like an awful lot to me, like 125, that's twice as much. So 1 to 2, 1 to 2, 1 to 2, 1 to 2. Yes? So that should be the balancing for that chemical equation. All right? This one here this one is a little bit, just a wee bit more complex. It says, what volume of nitrogen dioxide gas, okay, is formed when you take 350 milliliters of nitrogen with excess oxygen. Excess, the reason they told you that is just that they have lots of oxygen to use. So that's, we'll talk more about this in Unit 4, but basically you just have a lot of oxygen. So if you have way more oxygen than what you need, that's not really a factor in this, okay? How much NO2 can I produce from 350 milliliters is what they're really asking you. 350 milliliters of nitrogen, how much nitrogen dioxide could I produce? Well, 1 to 2, right? So 1 to 2, twice as much, 700, right? And that's law of combining volumes, basically. All right? Avogadro's law is exactly the same thing. Instead of talking about volumes, though, okay, in terms of volumes, milliliters, liters, we're going to talk about moles and molecules, but it's exactly the same, okay? So instead of seeing things like milliliters, liters, you will see moles or molecules. That's the only difference between them, really, okay? They're really one and the same here. So when you look here, for example, we had our balanced chemical equation right here. We would talk about 2 moles, 1 mole, 2 moles. Or if I said you produce, let's say you produce 8 moles of water vapor, how many moles of hydrogen did you have to use to get 8 moles of water vapor? It's the same principle, okay? But instead of using milliliters and liters, now we're going to use moles and molecules. That's the only difference. That's Avogadro's law. Okay, if I'm going to make 8 moles here, look, this is in a 2 to 1 to 2 ratio. So if I make 8 moles here, I have to use 8 moles here. And of course, if the question asked me, I'd say I'd use 4 moles here. 2, 1, 2, 2, 1, 2. Okay, same thing. Or we could just change the terminology. Instead of saying moles, we could say molecules. Okay. If I wanted to make 1,000 molecules here, for example, of water, well, how many molecules would I need to use from these other ones here? Well, 2, 1, 2, right? So 1,000, 500, 2, 1, 2. Okay? So same ratio, just different units. That's all. Okay? Let's just finish up one more thing here. This one here, real quick, and then I'll let you guys go. This is an example of Avogadro's law here. Look, pressure outside equals the pressure on the inside, right? Okay? If you're going to pump more gas into here, look, here's some gas, and I'm going to pump it into here, okay? You are increasing N, the number of molecules, yes? Okay? But look, what happens when you increase N here? You get more collisions, yes? More collisions equals more pressure. So this becomes much bigger than that. How are those two going to equalize again? The volume has to increase, okay? Until that this pressure equals this pressure here again. How does that happen? The volume has to increase. So think about this. Listen, just wait, guys. Avogadro's law, moles and volume, they're directly linked to each other. Look, here's how much gas I have, and here's the volume that I'm happy with. I put more gas into here. Well, right now the pressure is not the same as it was before. Remember, pressure and temperature have to be constant, right? The same in this case. So the pressures are not equal. How do you get the pressure to equalize out? Well, you've got to give it more volume, right? So that there's less collisions, so that the pressure inside of here is equal to the pressure outside again. So more N, more V. Okay? So just so you guys know. Okay, that's law of combining volumes and Avogadro law.